alternative to Zoom, to Zoom that I just want to make you aware of is Google Meet. I know that there are some issues with Google Meet, but I also know that Zoom hasn't been technically approved for JCPS use yet, although fingers crossed it will be. So I've put some links here if you're going to use Google Meet of some add-ons that might be helpful for you. Today we're going to use Pear Deck. So it's a Google Slides add-on for those of you who aren't aware of it. You can do live sessions and student-paced sessions so they can go through it on their own. You can do different types of formative assessments, which we'll be using today, so you can see that from the student side. I'll try to show you the Zoom from my side as well. As of right now, you can get a 90-day free trial for teachers. They keep extending that. So they had it at the end of last year, and then they said it was going to go away, and then they gave me another one. And so I feel like they're going to keep making it free. So everybody cross your fingers that it remains free because it's very helpful. It will be helpful to have two browsers open today because you'll have my Zoom screen, which I'll be showing some things on, but then we'll be moving through the slides on Pear Deck. So if it's possible for you to split your screen to see two at once, that's going to be the most helpful for you. An alternative to Pear Deck is Nearpod. I think it has much better capabilities and much better features. However, it's very limited on a free account. So if you have the possibility of getting this paid for, I think it's $120 for 12 months, and you can't pay month by month. It's just a one-time fee. So it's good to check out if you want more features than Pear Deck offers. So we are going to join Pear Deck now. You can do this two ways. You can go to joinpd.com and enter the code ZYDAZ, or you can go to the introduction box in the agenda and click to join session 3. So I'll give you guys a second to get to Pear Deck. We will use this for the rest of the first part of this session. So you can minimize Zoom, but don't close it or you'll be going through the slides without hearing what they're about. So just a little disclaimer for you guys. I saw this as I was going through some of the resources, and I thought that it was helpful to keep in mind. The physical and emotional well-being of students, educators, families, and communities are the priority at this time. So we know that we're all in a very big kind of transition phase. Leveraging the assets of home-based learning rather than trying to recreate school can provide meaningful science learning experiences that connect to students' home lives, interests, and identities. So I tried to, when I could, provide ideas for how to leverage some of the resources that students may have at home. Unfortunately, I do not have the time to tell you how to completely change your curriculum to be home-based, but I would encourage you as we go through this to just kind of consider what this might look like from a virtual setting and what benefits that may offer us. So to start, I want just some simple introductions. What subject do you teach, and what is your favorite concept or unit to teach in your content? So go ahead and share that now. All right, so if you want to look at my screen, I'm going to go through the responses that I've seen. If you're doing this as a teacher, you can share this screen and it won't have student names attached to it. There's a teacher dashboard that has student names attached to it. So chemistry, types of reactions, biology, environmental science, ecology, favorite content, ecology and evolution. I'm right there with you. Biology, evolution, genetics. This is my first year teaching. The Big Bang and composition of stars is fun. Physics, hard to pick. That means you're an awesome teacher if you love everything that you get to teach in physics. But momentum and impulse. Forces, favorite subjects are evolution and molecular genetics. Chemistry and physics, bonding. Physics, dynamics, and energy. New to secondary education, life science has always been my favorite subject. Biology, micro is my fave, though it's not a required unit, unfortunately. I know, I love to teach it as well. Conservation of energy, ecosystems, physical science waves. Okay, so we all have favorites, which I love. So keep that favorite in mind as we go through this today. And also think about and keep in mind your least favorite to teach. Doesn't mean you don't like to teach it, but what is your least favorite to teach? I didn't want to put that up here because I don't want us to ruminate on it too long, but I want you guys to at least think about it. So, all right, moving forward then. I want to just flash back to session 1 and 2 so that everybody can be kind of caught up on what we've done so far. In lesson 1, we just talked about engaging students in productive science conversation, trying to teach kids how to be okay with explaining and revising thoughts as they learn, giving them the opportunity to work with science at lower stakes. So having maybe a little mini lesson on just how to talk like a scientist, how to use CSW in the NTI world. We learned some new tools for NTI. We're working with some of those today and a couple new ones as well. And then how to model scientific communication and provide students with sentence starters to get them started off. And then yesterday we talked about grounding units in relevant and engaging phenomena. And I know that it was like a super fast crash course on this completely new way of teaching. And like I said, I would love to have like a whole week PD about this because it takes many days to learn. But if we can at least just shift our thoughts about teaching to be more aligned with this storyline way, I think that that will have a really big impact on our students. And as we go through our trial and error, we'll definitely grow in our ability to teach and plan this way. So some of the things that we learned yesterday was how to create storylines for units so that kids can trace the learning lines throughout the content. We compared what an anchoring phenomenon is, so something that anchors the entire unit and all of the learning, versus an illustrative or a lesson level phenomenon. We talked about framing a question based on observable events, so something that students can engage in and really get it invested in. We talked about more ideas of how to incorporate phenomenon into a unit. Someone said, which I love, that they love that storyline emphasis, the storyline of science content, and they'll continue to adapt that into their planning. Thanks for using the word adapt, because it's not going to be a fast process and it's not going to happen easily, and we're going to take some time. It's going to take some time. Phenomenon do anchor the lesson, can even help with the big ideas of the entire unit. Centering a unit around a central phenomenon can motivate students in a healthy way that may lead to more curiosity and easily create CERs and final projects that are innovative. And using an anchoring phenomenon helps organize science ideas and skills. So to kind of talk about that analogy that we used with the phenomenon yesterday, I don't know if you like analogies or not. They help me kind of focus and center my thinking about storylines. So we said that if we were building a house, just like we're building an NGSS classroom, we have to start with the foundation. And the phenomenon is the foundation that's going to kind of support our students' learning of science ideas. So then this frame that they start building is the science ideas. They're going to start putting science ideas onto this phenomenon. They're using that phenomenon to support their science ideas. So then the builders of this science understanding are the students. We are not telling the students why this science makes sense. The students are figuring out why the science makes sense. So then there's these elements, these things that threaten to tear our house down, right? And those are student misconceptions and these student ideas that kind of weaken their understanding of the science content. And so we have to figure out ways to make sure that students don't incorporate those misconceptions into the science understanding. And so what that means for teachers is we are not the ones constructing this house. We are more like the foreman. We can provide the materials. We can provide the kind of instruction on how this should be built, but we are not the ones building the scientific understanding. We already understand it. The students are the ones building it. And so to build this scientific understanding, students need these tools, right? And so those tools that they're going to use to build this understanding are the science and engineering practices. And so as we talk about science and engineering practices today, we're going to talk about them in the context of how students can use them to construct their understanding, to learn new science ideas, to connect old science ideas, and to build a solid house a solid science understanding. All right. And so I wanted to share some feedback from last session for two reasons. One is I want you to know that I see it, and I'm trying to adjust my instruction as I go. But two, I think it's important for us as we head into virtual instruction to be aware of what is difficult, even for adults, and so to prepare ourselves for what's going to be difficult for students. And so some of the feedback I got on the survey about the collaborative work yesterday, everyone was confused about what to do. No one was talking, and only a couple people independently worked on the model unit. I feel like a teacher again. So what I want to really encourage is, if you have questions, please let me know. I've gone through this, and in my mind, it's clear, but we know as teachers, sometimes it can be so clear in our mind, and it makes no sense to others. So if you have questions about what I'm asking you to do or how to do what I'm asking you to do, please let me know via chat or just unmute yourself and ask me. And I really encourage you to use the time to collaborate with these other teachers. I think that it can be very valuable time, which is why I've scheduled it in to each session, but it's only valuable if people are willing to talk and share and work together. So do your best to participate in those collaborative sessions. And then as far as the presentation, instructions for group activities not clear, I'm going to do my best today to make those more clear. Sometimes we were asked to choose prompts after they were taken down. I think that was with Poll Everywhere. I thought the polls had the question on them, but I guess they didn't. So something to keep in mind if you're going to use Poll Everywhere, to give your students time to really think about the prompt before you ask them to answer it. Cami group didn't do any collaborating. We're going to try it again today, and I'm going to give you more clear instructions. I enjoyed, but still fuzzy on creation, identification of all the different DCIs, PEs, etc. Hopefully that the glossary helps you a little bit. But I'm also going to talk with Lacey about maybe having a NGSS 101 for people who are maybe new to these NGSS standards and want to break them down a little bit more. Great. So that brings us to today, scientific practices to advance student knowledge. And our focus question, so the two things that we are going to try to answer with more information today. How can we design activities with SEPs in a way that engages and supports student sense making? And how does student learning change when they use SEPs to engage in well-designed activities? So hopefully by the end of the day, you feel like you can answer these with more information and a little bit more experience. So to get started, think of the activity that you most enjoy running or carrying out with students. So we've thought about the content that we really enjoy teaching. Now think about the activity that you enjoy the most. You don't need to tell me what the activity is, but what I want you to tell me is why you enjoy that particular activity so much. What is so enjoyable about that activity? All right, so what I'm seeing, students are engaged in the lesson and developing an understanding for what we learn in chemistry. They learn the rationale for something. The kids have that aha moment on their own and their own excitement over understanding. That's awesome. Throwing raw eggs at a sheet because students expect them to break. So it's kind of contradicting their previous knowledge, which is awesome. Hands-on, I can watch the students to begin to develop lines of understanding as they complete their lab. It involves students engaging in the process of science and seeing that their results match others, even though they explore different situations. Easy to set up, and students really like it. Don't we love those activities, the simple ones? Students are the lead, experiencing the aha moment with students, the most fun part. Observing the students figure out the next step or making decisions about how to proceed. Students are really engaged in the process and are making connections on their own. When students understand the procedure and run the lab in their groups, I'm trying to not cover up with my thing. Okay, I have students do 2 experiments and scientifically show the difference between constant velocity and acceleration. I like it because they're making the discovery and seeing it in action. All students are engaged. Students are able to make an abstract concept. There are lots of hands-on activities. Great. It's grounded in a very real issue. Fantastic. All right, so if we take this these responses and we think about what the theme is, a pattern that I'm seeing is that students are doing the discovering and students are having this moment, this, oh my gosh, I learned something moment. And so I know some people said like hands-on, but not everyone said it was hands-on. They really focused on the fact that students are making sense of something, which is awesome. And that's, as a teacher, really fun to see. And so if we think about the purpose of any activity, we'll skip that. It really is to allow students to figure out or make sense of a phenomenon, right? It's not for us to show them or prove to them, it's for them to discover. And for them to either figure out or to design and build, but it's for students to be able to make that, to discover that understanding. And so thinking about the purpose, first we're going to talk about what an activity is, and then we're going to talk about how we, what qualities make a science activity a good activity. So I know in science we often think of activities as labs, which are super fun to run, but an activity in science does not have to be a lab. An activity in science can be a teacher demo. It can be a proof of concept demo. It can be students designing their own study, working with secondhand data, doing a paper and pencil task that simulates real data collection, or paper and pencil activity not to collect data, but to understand a concept like a model. A computer simulation, different stations. An activity can really also be reading a scientific article. That can be a scientific activity in the classroom. All right. So when we say science activity today, we don't just mean labs. We mean really anything that's allowing students to discover. And so with that kind of definition in mind, what do you think are the qualities of an effective activity? What does an activity need to have in order for it to be effective? All right, so clear objectives, not too complicated, high student engagement, a hook or natural inquisitiveness, approachability from different angles, students discover and make meaning themselves, a driving question, clear expectations for the activity, to access prior knowledge students already have, student ownership and their concluding response, forces the kids to think for themselves, engagement and student driven, easy to understand, engagement cooperative, a real world connection or engagement, student interest, students are actively engaged, students understand what they are doing, engaged in problem solving. So I feel like the trend is student engagement, and I would agree. But sometimes that's easier said than done. And so today we're going to talk about what we really need to do to make our lessons engaging for students and therefore effective. So the key qualities that, and most of these were already listed, that I came up with: the objective is clear and meaningful to students, that it elicits one or two specific science ideas from students. It's not trying to hit all the science at once. It requires students to think about the science ideas and link them to other science ideas. And that in itself can be engaging because it's more purposeful to students. If it feels like it's just an activity we're doing and it doesn't have any real weight in what we're doing, what we're learning, then it's not going to be engaging for students. And so sometimes it's not what the students are doing that makes it engaging, it's what the students are able to do with what they learn that can make it engaging. And it moves students forward in their understanding of a phenomenon, either that lesson phenomenon or the anchoring phenomenon. And so we're going to start talking about designing effective science activities. And really, this goes for in the classroom and virtually, because the steps and the qualities are the same no matter what. And it's even more important that we hit all of these key features virtually if we're going to make this impactful for students. So the good news is you don't have to start from scratch. We're going to think about activities that we already run, and we're going to revise them to make them better and more effective. Now, there might be some activities that don't have these qualities and therefore maybe need to be removed from our repertoire. It's a grieving process when you have to get rid of an activity that you love, but I would encourage you to think about the activities that you do in your classroom in the context of the purpose and the key features, and really think hard about whether it's doing what you need it to do or not. Just because it's fun for students does not necessarily mean that it's useful for the development of that content storyline. So let's get started. The first thing we need to do is think about what phase of the storyline that students are in. And so we're going to flash back to yesterday. And yesterday we talked about this storyline development, right? And then at Next Gen Storylines, I shared this quote, and I said that this last part was going to be more useful today. So a storyline is a coherent sequence of lessons in which each step is driven by students' questions that arise from their interactions with phenomena. A student's goal should always be to explain a phenomenon or solve a problem. At each step, students make progress on the classroom's questions through science and engineering practices to figure out a piece of a science idea. And so we said up here at the top, we give them this anchoring phenomenon, this kind of conundrum, right, that is going to get them thinking about the content that we're about to teach. And then they're going to investigate that phenomenon with those science and engineering practices. They're going to think about how it relates to other things that they've experienced in the world. And then they're going to start asking questions. And so then the next step is to take one of those questions, and it's pre-planned on our part, and to look at a smaller phenomenon that can help answer that question. So that could be some data, that could be a model, that could be an article, a video, and we'll use those science and engineering practices to figure something out, to come up with or to discover a science idea or a DCI. And we'll hold on to that, and we'll move to the next question, and we'll do some more investigating, and we'll discover some more science ideas and some more DCIs. And then at some point, we'll figure out how all of those things connect. And once we connect them, students will have another question, and we'll start that process again until we've gone through all of the science ideas we need to come back up here and explain that anchoring phenomenon. So the example I gave you yesterday was as students are in their the biology unit for genetics, right? And so they see this anchoring phenomenon, these organisms, they're jaguars, that are spotted and some are black, and we think, why? Why does that happen? It could be where they live, it could be this, it could be that. And so we start looking at different phenomenon, and we learn a little more, and we learn a little more, and then we put that together. But once we put that together, we say, okay, well, now we know it's because of differences in proteins, but why are their proteins different? And so now we start down this path of looking at why proteins are different, and then we put that together, and slowly throughout the unit, students build up enough knowledge to come back here and answer this anchoring phenomenon and explain the whole process that leads to differences in organisms. And so the phases that we are going to break our units up into is the anchoring phenomenon, those investigative steps, and then the putting pieces together. So we have to think about what phase are students in. Are they just starting out? Are they investigating and trying to learn new science? Or are they trying to put science together? All right. For the purpose of today's PD, we are focusing on investigation routines. All right. That putting together is where the argumentation and explanation come in, and that has to be its own PD because it is extensive and it is complicated and there is a lot to it. And so I will say that I plan to have one of those eventually, but it is not planned yet. So TBD on when that comes. It's very important, but it is a very robust PD to be had. So we're going to focus on investigation routines today. All right, so once we figure out what phase we're in, then we need to figure out which science and engineering practices will be the most effective at this phase. And so the science and engineering practices kind of have their own purposes, and some of them can be used in different phases, and some of them really are only effective at certain phases. All right, so we have these 8 science and engineering practices: asking questions, defining problems, developing and using models, planning and carrying out investigations, analyzing, interpreting data, using mathematics and computational thinking, constructing explanations and designing solutions, engage in argument for evidence, obtaining, evaluating, and communicating information. And like I said, some of them come at different steps. So these things like asking questions and defining problems, or planning and carrying out investigations, those are going to be up there with that anchoring phenomenon for the most part. When we get into those investigation routines, we need students to use what we call the sense-making practices. And the sense-making practices are developing and using models and analyzing and interpreting data. All right. And so that's what we're really going to focus on today, is how we can use these two science and engineering practices to help students make sense of the science ideas when they are engaged in activities. All right. And so now comes the really important part. How will I frame the activity? What science ideas do students need to know or understand before starting? And have I made the objective clear? All right. And so what I want you to think about is how you set up an activity, any kind of activity, from reading a scientific article to running a lab. And I want you to read this quote because I think that it's very telling, and it really resonated with me when I first read it. Teachers get so caught up in making sure that students understand the procedures for carrying out an activity that they forget to engage students in talking about the purpose of the activity as it relates to the main learning goal and the developing storyline. And so if this is what the purpose of a setup is, take a second to just really take that in. Then let's think about what the key features are. You have some check marks on your screen. I want you to drag and drop them next to any statement that you think is a key quality of an activity setup in terms of building a content storyline. All right, and just so you know what I'm seeing, this is what I am seeing. I'm seeing a lot next to students discussing why they're going to complete the activity. A lot next to students think or make predictions about how their current ideas relate to the activity. Students discussing how the activity will bring them closer to answering the UCQ or DQ. Yep, those seem to be the most chosen. So here's what an activity setup is not. All right, and I want to be clear that this does not mean that you should not do these things. What it does mean is that by doing these things, you have not completed the framing of the activity for students within the storyline. All right, so we can do these things, and as far as behavior management goes, we need to do these things, but that is not an adequate setup for an activity. So telling students how to set up or conduct the activity, get students gathering the materials, teacher telling the students where to find the materials or how to complete a specific step, or having the students read through the steps and procedures. That doesn't place this within the storyline for the students. And so therefore, it doesn't really give them a solid purpose for doing it, even if we tell them what the purpose is, right? And so in order to set this up within the context of the storyline, we need students to think or make predictions about how their current ideas relate to the activity, how their current thinking relates to what they're going to do, discussing why they're going to complete the activity, asking or being presented with questions to answer through the activity, discussing how the activity will bring them closer to answering that unit central question or explaining that anchoring phenomenon. This is how we set an activity up to actually make it purposeful for the students. And if we don't do that, then we already lose a lot of that engagement that we wanted from students because it doesn't really have a purpose for them. And so just by looking at that, what are some things that you notice or that you wonder about what the examples and non-examples of an activity setup? All right, so I have some good comments here that I feel like are important to share because, again, it's a pretty big shift in learning. So we have having them make a hypothesis on what they think the result will be, student focused and connecting activity to the phenomenon or focus question. It is not all teacher run and directed. it is the students taking ownership. They will get frustrated if they do not know what is going on. I would think some setup or talk through is necessary. And like I said, the is nots doesn't mean that those are things that you shouldn't do. It just means that even though you've done those, you can't tell yourself that you've completed the setup, that you've given the students a purpose for doing this. And I would also encourage us to think about how much engagement students get when they are told everything they're supposed to do and aren't given the opportunity to figure out. So I know for me, I'm a perfectionist. I like things to be perfect, and I don't like mistakes. And so it took me a while to be like, they're going to make mistakes. Things might go wrong the first time, but isn't that part of science? Isn't that part of figuring out? And so while we like to have this control and we want our students to get the results that we want them to get, there is some learning that can be done from giving students a little bit more leeway and telling them that they have to figure out the purpose and they have to have this discussion before they can do this activity. Because if they don't understand why they're doing it or how it's going to help them, then we don't need to be doing those activities. In AP Physics, the is the goal or expectation of investigations. Students should have their procedures approved. I would agree with that. My question is, I wonder if the students are coming up with that goal or expectation, or if the teacher is giving the students the goal or expectation. That's my wonder. It should be student driven. And again, that doesn't mean that the students get to figure out how they're going to run the activity, because sometimes most of the time that's not feasible, right? But if we give the students the reason why and how to do it and why it's important, then we're not really giving them any reason to run it or to invest their thinking in it. So we can tell them how to do it, but before they do it, they have to think about why. I'm wondering how to make sure students will be discussing or to discuss their current ideas. And I think that's a little bit of, that's definitely on the teacher to make that a requirement. So in my classroom, you don't just get to run the activity. So that's not a given, that's not a right, that's a privilege. So if you can't tell me why you're doing it, and you can't tell me why it's important, and you can't tell me how it's going to help you just do this anchor or understand this anchoring phenomenon, then we need to go back and we need to start over with this anchoring phenomenon. If I get all the way to this activity and my students can't tell me why it's important, then there's no point in running that activity. They're not going to know why it's important afterwards if they don't know why it's important beforehand. Is nots are mostly teacher driven? Is our students driven? I wonder if consistent rituals, routines, teachers' expectations can streamline teacher driven components. And I would agree that this is something we don't start out the year by saying, by just giving them an activity, telling them to run it and asking them why it's important. It's definitely a ritual, it's a routine, and we have to think about how we can make this a consistent procedure. And that's something that we're going to work on today by looking at some units and really thinking about how activities are set up. I admit to being one of the teachers who has focused primarily on the procedures. I wonder if allowing the students to take on more of the leading role will give them a better understanding. I would say absolutely yes. Because you're giving them that opportunity to engage and be invested. Is students' focal points inquiry-based learning? Good. I wonder how to formulate and include an overarching question into an activity. That is going to come with that storyline development. So when we develop that storyline, we come up with an anchoring phenomenon, and then we think about what science ideas need to be learned in what order. And once we have those science ideas determined, we think of what questions students will be able to answer within each step, and that becomes our focus question for that lesson, which means that's the focus question for the activity within that lesson too. And so it's a lot of pre-planning, like I said, and I'll give you some resources later to help with developing those. All right, so any other questions or comments about that part before we move on? All right, so part of your task today, like I said, we're going to look at your first unit of instruction, and you're going to see if your activities really do include a setup that adequately frames the learning. And if not, you're going to think about how you can revise that, especially within a virtual world, to make it more useful to students. So the next step, we've done the setup now. What new understandings or ideas should students generate or deepen during this activity? And what's really important is, how will I support them in doing this? And how will I know if they do? And so, again, another quote that resonated with me when I first started learning about this activity design: too often, students can simply follow procedures without thinking about the science ideas embedded within the activity. If we've laid this out so perfectly that students can just read every step and do it without thinking about it, then that's not useful to students. It should require them to think and to problem solve and to make sense of something as they go. And so that's going to be our focus in the second half of this session today. And we're really going to focus on how we support students when they are using SEP2, which is models, and SEP4, which is data. Because there are some ways that we can support sense making as they're using those, which will make that activity much more effective in developing that storyline. And so we'll return to this in the next step, and your focus will be, how are students being supported in sense making during that same activity that you analyzed with the setup? All right, and so then finally, and this is actually the most important step, I would argue, and probably the least used in classrooms, or at least the least used effectively. And that is thinking about how the students will link the learning from their activity to the rest of the unit. And how we will support them in doing that. And how will we know once they've done it? And so that is where the activity follow-up comes in. All right, we follow up the activity by focusing on linking the activity with science ideas and the science content storyline, that anchoring phenomenon. All right, and so if that is our goal, again, drag and drop, which of these are features of an effective activity follow-up? Awesome, I have a ton next to students explain and discuss how their new understanding links to other lessons and science ideas. A ton next to students explain and discuss how their new understanding connects to the storyline, unit central question, unit driving question. Students explain or discuss the new understandings they gained and how their thinking changed. And students use new ideas to make predictions about other phenomena. That's where I have the most checks. And so let's talk first about what it is not. And I want to say again, this does not mean that you should not be doing these things. It just means that by doing these things, you have not finished framing this activity within the storyline. So teacher tells students how to clean up and return materials. Yes, you should do that. No, that does not help students add on to their storyline. Students explain or discuss their results. That should be part of the activity. That is part of that science and engineering practice in analyzing and interpreting data. So that's still part of the activity. Doing that does not mean that you have framed that activity within that storyline or told student or asked students to connect it. Teacher tells students what the correct result or outcome was. While sometimes we need to do that, that does not frame the learning for the students. And students explain or discuss the errors or shortcomings of the activity. Again, that is part of the SEP. That is part of analyzing and interpreting data, but that does not place that activity in the storyline. And so what it is students explaining or discussing the new understandings they gained and how their thinking changed. Remember, in the setup, we have them make predictions about how their current thinking relates to the activity. So naturally, in the follow-up, they should reflect on what they thought and how that thinking has changed. How their new understanding links to other lessons or science ideas, how their new understanding connects to the storyline, unit central question, unit driving question. And then they use those ideas to make predictions about other phenomenon or about the current phenomenon. And so that can be as simple as literally asking them these questions after an activity. But if we don't do that, and I am so guilty of having done this for a long time, of just assuming that they have made that connection. Because to me, it was very clear. Well, of course we ran this activity so that they would know this, so that we could answer this question. But making it explicitly clear to students is the most important if we want them engaged in activities. And if this becomes a routine, if students know that after every activity, they're going to have to tell you what they learned and how their learning changed and how it made sense and how it helps them get closer to explaining the anchoring phenomenon, then they will inherently become more invested in those activities because it has a bigger purpose for them. And so what do you notice or wonder about this follow-up? So Natalie asked if I do this in written form or verbal form, and I do both. So most activities are either partner or small groups, and they have that, they will have written questions that they have to answer within the activity, and then they can talk with their partners, they can answer it there, and then I'll do a whole class discussion where I ask similar questions again, and we have that discussion again, because inevitably there are going to be students who are going to be it's going to be more challenging for them to make those connections, but it's important to ask students to do it on their own before you do it for them or do it with them, because that really places the responsibility on them and gives them that challenge. But I would say you can do it either way, and one way is not necessarily better than others. Throughout the activity, I will also circulate and ask those questions to students that I know they're going to have to answer at the end as they're doing the activity, and that's also helpful. I want to share again because I have comments that I think are really important to discuss. So, places ownership on learning firmly into the students' hands. Teachers are no longer telling you what you learned, which is difficult for students because they are used to being told what they should know and what they should have learned and what they should do. And so I want to think back to the first session in this series where we talked about getting students to communicate in scientific ways, and getting them to be comfortable sharing their thoughts and comfortable sharing their ideas, because that means that they're getting comfortable thinking for themselves. And so it's a whole shift in classroom culture that you are going to have to foster with your students. And it doesn't happen easily and it doesn't happen quickly. But it's something that's very important to do because students come into us having been through school, for the most part, being told what they needed to write down and what they needed to remember for the test and having to answer multiple choice questions. And so we have to support them in shifting their way of learning. So students are reflective learning, getting all the activities to line up. I wonder what is the best way to address students who just clearly cannot understand the purpose behind completing the activity at the end. In that regard, I would say they shouldn't have run the activity in the first place. All right. So if you have students who can't tell you the purpose before they run the activity, then, and you'll have a small group of those students, then that small group needs to be with you. And if all the other kids understand, now if it's the majority of the class that does not understand the purpose, then we need to backtrack. And we need to make sure that all the science up until that point is clear and that the storyline up until that point is clear. We can't just truck along and say they'll know it after they do the activity. If they can't tell you the purpose before you start, then that's not the time to run the activity. If it's just a small group of them, and we're setting up this activity and they just cannot tell me, then that small group is going to be with me. And we're going to have some discussions as we go through it. We'll have some discussions before we start, and then it will be a much slower process. Maybe I'll be the one doing the actual activity and just asking them questions, because sometimes it's just that they don't really care to learn the purpose or to think about the purpose because they just want to do the activity. If they start to learn that they can't do the activity unless they understand the purpose, then again, that's a motivating factor to really start understanding that storyline. It puts more emphasis on the student doing some higher order thinking. Again, students making connections. The is helps them take information to a deeper level and connect the content to the overall picture of what we're studying. is not merely focused on isolated lesson or topic. It opens the door to the next thing, or at least a way to expand. And if we open that door to the next thing, then whatever that next activity is, we already have more student engagement because they already want to know the next thing. Repetition and restating what was learned. I wonder what this would look like in the classroom. How is it incorporated into the lesson? It's just what we do after every activity. So anytime we read an article, anytime we look at data, anytime we do a model or a lab, we have, the actual doing is a small part of the lesson. The discussing is the bigger part of the lesson. So whether that be them discussing with a partner and having written explanations, or discussing with a group, or discussing whole class and charting, or coming to a group consensus, whatever it is, that is, the follow-up is the majority of my lessons. The activity is not usually the majority of a lesson. I'm wondering what format this usually takes. I've tried full class discussion and individual writing with varied levels of success, but I'm not pleased with how I've done either. We're going to look at some tools today that they can use during these sense-making activities, and those should help with those follow-up, with the follow-ups. The underlining theme is students explain. I wonder if we often stop short of completing the process because we see the is as extensions of an activity rather than the purpose of the activity. I would say, yeah, I think I stop short in activities a lot and think, well, they got it. They said what they got the results they needed. They must know, we're moving on. And then I ask them to explain later and I'm like, why did we run this activity? You guys can't tell me anything about it. So yeah, we do. We stop short a lot. Follow focuses up on self-reflection. Teacher would start a class with a question that students would write and answer as an opening. Yeah, that's their prediction. As an exit, the students would answer the same question in writing. I've repeated the concept with a similar but different illustrations. Love that. Give students a chance to really digest. Awesome. Yeah, and not just vomit out some real knowledge. Yes. Awesome. All right. So what we're going to do next then is, oh yes, part of, yeah.
I have a quick question.
Yeah.
What about kids? I've had issues where like I'm doing activities and kids are like, oh, I've totally done this before. Like, and not the vast majority has done it, but like I have a few here that say, oh, I've totally done this activity. How do you handle that?
I ask them what they learned from it. And then I ask them how that applies to what we're learning. And I would venture to guess that the majority of the time, they can't answer those questions. And so I say, if you can't tell me what you learned from this and how it helps you explain our anchoring phenomenon, then I think we need to try it again.
Okay, awesome. Thank you.
And if they can, then they can write about it. That's great. They can write about it while everybody else does the activity.
Yeah.
Yeah.
Thank you.
Yeah, you're welcome. Good question. All right. So before we get to analyzing our own lessons, I want to analyze two lessons together to see if we can find the setup and the follow-up and the tools for sense making. So we're going to use something called Pinup. It's going to look like this. And on the left-hand side, there'll be a document that you can look through. That document is the lesson with the activity embedded in it. On the right-hand side, I put some Post-it notes with questions on there. They're different colors. So the first one will be yellow, and it'll ask you about the setup. And then you'll click this little plus button on the right, and that'll add a Post-it note to the board, and you'll put your answer there. And then I just ask that you make your answer, your Post-it notes, the same color as the question, because there's 3 different questions. That way I know which one goes with which, if that makes sense. So you're going to answer the prompts on the thing by, on the board, by adding pins of the same color as the question. Sometimes it takes a second for the pin to show up, so be patient. I clicked one time and then I ended up having like 3 Post-it notes pop up at once. So this is a shared board, so all members can see your posts. You are also able to edit my postings, so careful not to delete part of them, just so that you are aware. So what you're going to do is go to the agenda. And on the agenda, you will see the Pinup lessons highlighted green. There's a lesson A and a lesson B. You click lesson A. That will open that first Pinup. And I'll give you a minute or two to read through the document Um, and then you can add your pins. All right, we have more people than I had in the last sessions, so I am going to actually share the original document with you so you can access it and read it without moving it all around, if that's helpful, and then just post your pins on the pinup, if that's clear. So the activity document I've put in the chat, and you can open it there and read through it there if that's going to be more helpful for you. All right. I'm going to share the original document, and you guys can make copies of these with that link in the agenda. So the lesson concept: students use a simple balloon model to visualize the Big Bang, then read about the beginning of the universe. So this engage part is to get students involved in the lesson, but it isn't necessarily getting them involved in the activity yet. And so if someone wants to unmute and tell me, what is the activity of this lesson? What do you see as the activity of this lesson?
I mean, isn't the activity here the actual like inflation of this balloon, and drawing the balloon and then analyzing like what happened with the balloon and how this is an analogy for the universe?
Okay. Yep. Others, what do you guys think? Agree, disagree? Add to? Chris agrees. Thank you, Chris. Awesome. Okay, so if that's the case, then the setup in this is they need to think about why that's important, how it is going to help them understand something. And so the setup as it is in this lesson right now is asking students how we know about things that we cannot directly observe and relating this idea to scientists rely on evidence to make inferences about how the universe was formed. However, on the pinup, somebody said, I think the setup would include an explanation of how the students thought the balloon or confetti would tie to the universe, predictions on what they thought they would see from the demonstration. That is an excellent addition to the setup that I would agree needs to be included. The setup as it is right now does not fully link the activity with the purpose within the storyline, right? So then they run this activity, and once they run the while they're running the activity, I want you to look for what supports there are there to help with students' sense making. And so if we look at this pinup, which got a little bit messy, let's see. That's the setup. That's the setup. Here we go. So students should be able to collect data in an organized way. All right. Does anybody else want to either unmute and share or send in the chat what else is being used to support student sense making during this activity? All right, give me a second. For some reason, my Zoom chat isn't pulling up. There it is. Comparisons of 3 models. Okay. Anybody else? What are students given to support their sense making? Or what are students supposed to learn from this activity? Let's start there. What are students supposed to learn from this activity? What science ideas should they gather from this activity?
The expansion, that originally everything was closer, and over time it expanded.
Okay, so yeah, of the universe, right? Originally everything was close together, and then over time it expanded, right? Okay, so if that's the goal, we're using a balloon, which is not the universe. And the universe is something that's very big and hard for students to grasp, right? And so we're using a model, and the model is this balloon. And so what steps or what tools is the teacher using in this activity to help students make sense of how this activity represents real life?
Sorry, after you.
No, go ahead, Michael.
Students needed an analogy, like an explanation of the analogy here, right? So we need to know, like, what the balloon represents, what the dots on the balloon represent, what the confetti represents. Right?
Okay. Yeah, Scott, is that what you were going to say? Do you want to add to that?
Well, I was going to add to that the students have, along with what Michael pointed out, they also have the prior knowledge of having seen balloons before and understanding that when you blow them up, they get bigger. And I think that it is a need, but I think that understanding what prior knowledge needs to be accessed in order to achieve how a model functions is helpful.
Okay. Yeah. So we need to choose a model that is going to make sense to them, that's not also going to be confusing to them, right? So we choose this balloon because they know how it works already, right? And then Michael said that they need to be able to understand what that balloon is supposed to represent, right? So in our minds, we might think, well, of course this balloon represents the universe. That's what we're learning about. In our students' minds, they're like, well, it's a balloon. It blew up. Like, that's what happens with a balloon, right? And so if we look at this activity, there is a specific tool that the teacher uses to make sure that students are able to make sense of this activity and this analogy. And it's this analogy map towards the bottom, where it has like the part of the model is or are like part of the real world, and they're alike because. Does everybody see that analogy map it's on the very last page? Okay. So can anyone tell me why they think that analogy map is essential?
Because all of the models are going to have some kind of limitation to them, the analogy map helps the students make that connection from what we're doing in the classroom to what it's actually representing outside of the classroom. Especially, we used them a lot. I taught integrated science at the physics component last year, and we used them a lot with that because otherwise they don't get it. When we're using the water chamber and we're putting in the food coloring of different temperatures, they're like, oh, this is really neat, but they don't get that connection to what's happening inside of the earth unless we use that analogy map to help them tie it all together.
Exactly. So the students are engaged in the activity, like you were saying, but they're not engaged in the storyline. They're just engaged in the activity, right? And so that's not really helpful to us in the end. For a day, it's fun and we get really good participation. But after that, then the next day, we get less participation because we're asking them to apply all these science ideas that they never really actually thought about before, right? And so when we're doing these activities, we need to think about the activity itself. We're going to get engagement from, but what tools are we going to use to support them in also engaging in the storyline that goes along with this activity, or that this activity goes along with. And so once we have that, the analogy map ties the activity to the phenomenon or storyline. Exactly. And that's the actual sense-making portion of this activity. And so when I say what tools do we use to support sense making, what that means is what tools are we using to support students in making that connection to the storyline and actually making the connection to the science. And so, so they conclude the day with them making, so what is helpful, before you run the activity, they need to know what this model is going to represent, right? So there are part of this analogy map would need to be completed before you run the activity. So that part where we have the balloon and the dots on the balloon, students need to know what that represents before we do it so that they can relate what's happening to the science part, right? And now afterwards, and we can add columns here, adding that air to the balloon, what did that represent? Those things can happen after we do the demo or after we do the analogy, and they're going to be more likely, to be able to answer this part because they will have been thinking about it in the correct context as they do the activity. Are there questions about that or comments or thoughts? Okay, and so then the follow-up that we have is these questions down here. What components were in that model that are missing from yours? What is in yours that was not in the original model? And why do you think we used two different models to demonstrate the Big Bang? And then we should probably add more to that follow-up if we're going to frame it within the storyline. So can anyone maybe share their ideas of what else needs to be included in that follow-up to make this activity as effective as possible?
Brittany, can you ask that again? I was distracted by my daughter.
No worries. Yeah. So what else do we think that we should add to this activity follow-up to really frame it within the storyline and make the activity effective? And I've put the follow-up back up on Pear Deck. Or do we think it's good?
One of the things that we do a lot at the end of our lessons is we have them go back to whatever their prediction was and reevaluate it to see were they correct with their prediction or were they not.
Mm-hmm. Awesome. Any other thoughts? And so I highlighted there in the pinup about the setup. Someone had wrote, I think the setup would include an explanation of how the students thought the balloon or confetti would tie to the universe. And so going back afterwards, looking at that analogy map, looking at what they originally thought and making any revisions, and then maybe writing more of an explanation and explaining how their predictions either were or were not like the actual activity will help them really get into that reflective mode and help them tie it to the content storyline. So what I want to do now is look at a couple other tools that we can use when using models to help those students with that sense making. So the one that we saw in this activity was an analogy map. And I'm back on Pear Deck now, right? So we have an analogy map. We have the components of the model. They are like whatever part of the real world it's supposed to represent, because, and how are they not alike? And then at the bottom, you can see how do these components interact, or how did these components interact? And so that would happen after the activity. And so if we're using a model to represent something that is too big or too small for students to see, we really need to make sure that they understand what that model is supposed to represent before we begin. And so in that case, a component map or an analogy map is very helpful. If we're going to do this digitally, it's very easy to make this into a Google Doc that students could fill out. Students could, I've had them do it before, just write it out on paper. We know that they probably haven't picked up a pencil in a very long time, so having them write some things out on paper is never a bad thing. And take a picture and upload it. That's always an option. You can use Kami if you feel like you are capable of using that interface. You can assign those individually to each student. That way they can annotate in multiple different ways. Kami really does have some really good features. And in the agenda, I did put a link to what features are included in the free version of Kami. So you get 30 days of all features. And then after that, you just get some of the features, but there's still some really good features in there, and even on the free version. So I would recommend looking into that. It's very helpful if you want students annotating or marking up or something like that. It's like Google Docs, but with more features. Another thing you can use if you're going to be working with a model throughout a lesson or even throughout a couple lessons is this before, during, and after. So if you have students try to draw or represent what is going on in an anchoring phenomenon right at the beginning before they've learned anything, and explain below what their drawing represents. And then once you've gone through a couple lessons, come back and have them draw what they think again, adding some more science ideas into it based on what they've learned and writing an explanation of what they drew, and then come back again at the end of the unit and have them revise and draw again. If you have a model that you're going to be using throughout, then this can be a very helpful way for students to actually see their thinking change. And that's a really powerful thing for students because sometimes they forget what they used to think. And it can be fun for them to come back and be like, oh my God, I drew this, that's crazy. And you're like, yeah, but look how much you've learned. So this is an example that I found. Here was the initial drawing that a student made, and they had their little explanations over here on the side. And then the final drawing, you can see that there is so much more detail. There's so much more going on, and that's a really cool way for students to see how their learning has grown, but also for them to keep track of what's going on in a storyline if something is too big or too small for them to actually see. So some ideas, again, you could make it into a Google Doc. Students can write it out, upload the pic. You could use Kami. This one, I think it would be super cool to use Flipgrid because they can take little videos of themselves. And so if they did a Flipgrid at the beginning explaining what they drew, and then they did a Flipgrid at the end showing what they had drawn at the beginning and then explaining how their thinking changed, that would be a really cool way for an interaction to occur. And you could even have assigned students to watch other students' videos and comment on it. They can do videos back and forth if you put them in like little small groups. That could be a way to encourage interaction and for students to share their ideas and show how their thinking has grown. Another idea is this predictions and outcomes. So in this case, you've given students the diagram and they're going to annotate it before they do the activity, what they think is happening at each stage. This is just the only online example I could find. It's not a very great one, but you get the idea. They're going to write down what they think is happening in each of these stages. And then once we do the activity and we discuss the science, we come back and we redo or annotate again and discuss how our thinking was different from what actually happened in the activity. So we have that setup, making predictions, and then we have that follow-up explaining what actually happened and why that happened. And I've put the prediction model and outcome model here, not necessarily because you need these pictures, but because the directions are different with the setup. Oh, it's not showing my illustrations? Okay. Can you guys see my illustrations? The pictures on there? Yeah? Okay. Well, I want to open this anyway, so this will be, oh, nope. Okay. I do want to show, okay, it's not working. So I'm not going to show it right now, but you can see that the directions for the setup model are different from the directions from the follow-up model. And so students are going to be asked to do more in the follow-up than they are in the setup. And so that's going to show us what learning has taken place, but it's also going to show students how their learning has grown or changed. My NTI options for that, again, Flipgrid, I think is really cool for having students explain the changes in their thinking. Zoom in models are very cool for things that are too small. So if you draw, maybe give the students the diagram of the general picture, and then have them zoom in and show what's happening in different parts of that model. That can be very helpful in giving students perspective. Because if we're looking at something that's really small, it's hard for students to kind of get that perspective. And so zooming in and really showing them like, this is what it would look like under a magnifying glass or even smaller can be helpful in giving them that perspective. One feature in Kami is you can upload a blank page, or you can just upload a picture. And so that can give students the opportunity to annotate that picture or draw on a blank page if you prefer that. And then I wanted to include this. Sometimes your summative assessment can be for students to draw a final model of whatever phenomenon that the anchoring phenomenon was. And so it's very important that if we have them drawing models to demonstrate knowledge, that we give them some kind of rubric or some kind of goal. And so I wanted to include this, and the link is at the top, so that you can give students this and you can edit it. It's a Google Doc to align with whatever you want. But just to point out that it's really important to make sure that students know what's expected of them so that they can demonstrate the learning that you're expecting them to demonstrate. And then lastly, there's just a lot more resources that I have. So I don't want to go through all of them right now. Here's a link to other instructional strategies for supporting students in developing and using models. I tried to come up with some substitutes for things that were mentioned in here. So like doing a gallery walk or sticky notes, you could use Jamboard, Padlet, or Pinup. All three of those are similar to, or can be representative of doing a gallery walk or having students post sticky notes. Oral explanations, I would recommend Flipgrid. Any type of annotations or drawings, I think Kami is the best option for that. Developing models on paper and upload a pic, I think it's good for students to still be writing, or use Kami or Google Docs or Slides. All of those are virtual options that you can use. All right, so lesson B is going along with SEP4, designing and analyzing data. And to kind of streamline this, I'm just going to share the I'm going to share the link to the original document in the chat, and you can look at that, and then you can go to the Pinup and post what you think the setup is, post what you think the tools to support learning are, and post what you think the follow-up is. And this is a student worksheet, so there are no teacher instructions here. It's just what the students are doing. If you aren't sure how to change the color, I've shared my screen here. You should be able to click on the Post-it note once you've added it, and then click this button right here, and it should pull up the different colors, so you can change the color of the Post-it. All right. So the SEP that we're looking at is analyzing and interpreting data, which is SEP4. And so the activity that they're doing that revolves around SEP4 is looking at this graph about the percent of fish in a population sample with full and low body armor. Okay, and so the goal of this activity is for students to understand the rate at which this population changes. So we can see that it's not an immediate change, which we'll talk about the science ideas behind that in a second. But so they need to analyze and interpret this graph. Okay, and the science ideas that need to come out of this is that it took multiple generations for the population to change. That the population never reaches 100% of either trait, and that there's more than one variation of the trait in the population. Okay, so to set this up, we need students to be thinking about those ideas before they actually look at this data. And so to do that, we have this setup where they think about these science ideas, about the population changing. The individual fish that is not part of this activity, but it's setting up another activity that comes afterwards, about variations decreasing or increasing, variations being favored, and how long that change takes to happen, right? So this is our activity setup where students are thinking about science ideas. And this science content storyline, or this anchoring phenomenon, is a stickleback population. So they're thinking about those science ideas in the context of this anchoring phenomenon. All right, and they're making some predictions about, using their current knowledge, about how those science ideas relate to this population. All right, and then they're going to analyze the data. Now, we can't just give students data and expect for them to find the important patterns or trends within it. So what is the tool used here to help the students in making sense of this data? The tool or strategy. You can send it in the chat, or you can unmute.
Students are being guided through, this, exactly what's in the chat, these what I see and what I think trends, and how to annotate this graph really nicely.
Mm-hmm. Yeah. So the way that we support students in making sense of this data is doing something we call a WIS-WIM caption. So first, we just ask students to draw arrows to points on the graph that they might find interesting or that they might have thoughts about. Usually we say patterns, trends, or significant changes or differences. And then they're going to think about what they think it means. Now, I will tell you that I used to just ask students to write what it means, and I had a really hard time getting students to answer that. But then I asked them to write down what they think it means, and they were much more likely to write that down because they didn't have to be right. And it was great. I literally added a word. That was all I added, but it changed the whole take on this process. And what it helped me do was understand, or to see where students were struggling, because this is a skill. And so it wasn't actually that they didn't understand the science. They were struggling with the skill of analyzing and interpreting data. And so this WIS-WIM caption was helpful in supporting students in making sense of this data and what it actually means, and understanding the science behind it. And so once they were able to do that, then they could take those science ideas and they could apply them to the storyline, which is what that follow-up is down here at the bottom. Refer back to the table you completed for the two scientists, and based on the new data that you have, right, which really means the new science ideas that have come out of this data, determine if you can add any information to your answers. And then they also go back to this table and they see if they can change anything in this table based on those new science ideas that they have. But those science ideas were elicited by breaking this analysis and interpretation down for students and supporting them in really figuring out what this graph even means. And so that is a whole activity. Just this graph is a whole activity. And so every piece of data that you give students needs a setup, and it needs a support, and it needs a follow-up if you're going to make that data meaningful to the storyline. Are there questions or comments about this activity or this lesson? All right, so a few other supports that I have. So this is the WIS-WIM caption that we looked at within this lesson. A few other supports that we can use, especially when we're just starting off with data analysis, one thing that has been very helpful for me is doing these group observation, partner discussion, and individual summaries. So I give students a graph and I let anybody share out what they see. Anybody can share out what they see. Some people will just say, I see that the line goes up, and that's great. So we write it down. We see that the line goes up. We see anything we see, we write it down. And so students can record anything that was seen. And if there's something that goes along with that, like I see this and it means this, they can write that down too. So they're getting input from their entire class. And so then we do a partner discussion. So I'll have questions to kind of guide them through the next step of analysis. Those questions can be whatever you think is important, whatever you want to draw students' attention to on the graph. So it could be, what trends do you see in the graph, or what patterns do you see in the graph? What seems odd in the graph? Where does the graph end? What percentage? Whatever you want, whatever you think is important, definitely important for students to notice. Okay, they do that with a partner, and then on their own, they're going to summarize how that is important to the storyline. And so they've got lots of help in looking at the graph. They've gotten to discuss it. And you've drawn their attention to the important parts of the graph, and now they are responsible for tying that to the storyline or the phenomenon within that lesson or within that unit. So write a summary, then explain how this graph helps us answer the focus question or the unit central question, or explain the phenomenon. And so that's a very helpful way to start with analyzing and interpreting data. Natalie said, I feel that I have to give a primer of the graph basics as a mini lesson before data analysis. Yes, it can also be just, it can be kind of part of your routine. So maybe when you start out giving graphs at the beginning of the year, we identify what's on the x-axis, what's on the y-axis, what type of graph, and that's just something we do every time. And then we can phase that out as we get farther through the year. But that's definitely something, and everybody's gonna, I have some AP teachers, I have some freshman teachers, some junior teachers, so everybody's gonna be at a different place, but it's important to think about what routine you want to establish from the very beginning for data analysis, and then where you kind of wanna end up. And so you can scaffold that learning through an authentic experience. So instead of just giving them graphs that have no meaning and asking them to analyze it, when we give the first graph to support the first anchoring phenomenon, we have this routine that we're going to follow, and that's going to help them tie it into the storyline. And then in the next lesson, when we give the graph, maybe we take one step out. So maybe they have to identify the X and Y axis on their own. And so you can make that progress, but it can be in an authentic way instead of having to have that unit at the beginning of the year where we talk about how we analyze data, and it really doesn't apply to any of the lessons that we're teaching. So data analysis sentence strips is another one. So you can give statements about the data to the students, and some of those can be correct and some of those can be incorrect. And you can go about it two different ways. You can have them choose the correct ones and they can circle it, or if they're movable, if they have the strips, they can move them. Or you can have them choose the correct ones and make the incorrect ones correct. And so that's just another kind of step, kind of a scaffold that would come once you feel like they're a little better at analyzing data. But that's another helpful support in getting the students to analyze and interpret data. And if you're giving them those sentence strips, then you get to determine what information they're seeing. So if there's something that's really important for a really important science idea for them to get out of this data, you can put it in those sentence strips. And that way they're seeing that in a way you are telling them, but you're not explicitly telling them this is what you have to know. They're still having the opportunity to discover that. You're just giving them the support to discover it until they can do it completely on their own. So again, here's another link to even more strategies. I pulled out the ones that I feel like are the most helpful in my classroom. Again, I have the NTI substitutes here. And I want to give you your task for today. You won't have a lot of time, but you can at least look at one activity. But before we do that, I want to know if there are any questions, concerns, or comments. about what we've done so far? Again, I know that it's a crash course and we're moving really quickly, but I feel like if you at least have the tools, then this is something that maybe you can do with a PLC, or it'll help you when you're looking into your own units and deciding what to teach. So you're going to access the first unit of instruction. If you were here yesterday, it's the same exact unit, except for physics. I changed physics based on the conversation that we had yesterday. So those are in orange. You'll click the one that applies to you. Find the first activity. I have highlighted it light blue in that document for you to look at, okay? And as a group, you're going to determine what is the setup, what is the activity itself, what is the follow-up, and what are the sense-making tools or supports that are there. Now, these are not necessarily exemplar units, so you're gonna need revisions and you're gonna need additions, but you at least have somewhere to start so you don't have to start from scratch, all right? I think you can just disregard this activity planning template as far as your group purposes go, but I did put the link in there for you to look at on your own time if it's going to be helpful to you. What questions do you have about the task? If we look at this document, let me pull up the biology one. So I know that this is a big unit. It was the most developed one I could find, and I feel like it has a lot of good resources, but I know it also takes a bit to look through all of the resources. So the question that they are needing to answer in this one is, what explains why the population of buffaloes in the Serengeti changes so much? So that's the question that we need for them to answer at the end of this lesson. So they're going to watch a short clip of Serengeti highlights, examine a map of the Serengeti and photo capture data about the animals that live there. Finally, I read a short passage. So the setup in this case might be there in this data that they look at. This graph that you see, oops, I didn't mean to tap that. The graph that you see right above the blue highlight, it says buffalo in the Serengeti increased from 1961 to 1975 and decreased. So your setup could be to have them look at this graph, to share their findings, to link that to things that they, to other phenomenon that they've heard about. Maybe they've heard about increases or decreases in populations of other organisms, and then get them to ask questions. So if you get them to start asking questions, then that is how you can start this storyline. You can get them to originally be engaged in this storyline. And so once they're engaged and they're asking questions, now we can watch this video clip and examine those maps and stuff like that. So that's kind of the setup to the whole phenomenon. Does that make sense?
Yeah.
No?
Yes.
Okay.
Yes, that makes sense.
Okay, and so then I guess so if you have that setup, then what you need to think about is, what do you want them to get out of watching this video clip? What do you want them to get out of looking at this map? What do you want them to get out of this passage? And then what do they need to do with that knowledge once they have it?
So I guess I'd want them to get that populations change over time and different things can make them change over time.
Sure. Yeah. And since this is the first lesson, we're really just getting them into that anchoring phenomenon, getting them invested in that anchoring phenomenon, so that can lead our way through the rest of the unit. So yeah, if that's what we want them to get, then we need to think about what are we going to do to get them there?
So I guess they would have to understand what limiting factors are and things like that, that sort of control populations, like birth rate and death rate and all those sort of population dynamics.
So do they need to know that now, or is that what they're going to need to know to eventually explain this phenomenon? Do you see what I'm saying?
I think finding a short video on this particular species and the initial introduction of what this species actually is. And because some kids may not even be familiar with, you know, I'm assuming we're talking about a Cape buffalo here in Africa. And most of them have just seen, you know, the migration and everything like that with, you know, the Nile crocodiles eating them and things like that, lions eating them. So I don't think they really understand, you know, probably very few of them understand the whole concept of populations changing other than the fact that other animals prey on. And you need to introduce them to other things that may be factors in regulating that population and why it's necessary ultimately.
Yeah, and we don't want to get ahead of ourselves. This is the first lesson, right? So all those things you're saying is true. Those are all things they need to eventually know. But right now our goal is to just get them to start thinking about those things and start being interested in those things so that as we move through the lesson, they're interested in learning those things that we're going to teach them.
Agreed.
Right. And Natalie, correct. The setup is really narrow. The setup is really just about each individual activity and how am I going to set this up to make it feel important to students? And then to make it feel important to students and the storyline. And then what do I expect them to get out of this activity and how are they going to link it? And then we move to the next activity. And so the setup, you can have a broad setup for a lesson, but the setups we're looking at are each activity and how each activity is going, how we're going to frame that activity to make it worthwhile to students. I feel like you guys you're starting to do it. You're asking the right questions and you have the right ideas. I need to jump over to chemistry, but if you need me again, just ask me for help and I'll be back.
Of like a little, like a sled. It was like a rocket powered sled was one thing that I used for this standard. So you could add forces in different directions and like change the mass and such. Does that seem like the kind of thing we're looking for here?
If this is a lesson on Newton's second law, ultimately, I think those are things that they would probably discover in later lessons, or maybe that would be an activity that would come as they develop those ideas. So, Brittany, I'm having trouble getting into Cami. It's just spinning I've never used it before.
Okay.
So I clicked on it. It wouldn't let me do anything without signing up, and I'm clicked on sign up, and it's just spinning. So I can't see anything.
Can you? Okay.
And I don't want you to spend this time helping me with that so much as I just want you to be aware that may be an issue people have.
Okay. Thank you for letting me know. I'll see if I can figure it out for you.
You're welcome. And don't go on doing what you need to do for the PD.
Okay.
Figure it out later because we don't have much time left.
I know. Thank you for letting me know.
You're welcome.
Thanks for coming back, guys. I wanted to let you know I did last time too. If you guys want to stick around to ask me questions or to bounce ideas off of me or run something past me, I will stick around. I like to honor everybody's time. I said it would end at 11:30, so I want it to end at 11:30, but I don't have anywhere to be, so I'm happy to stick around, answer questions, clear anything up that you might need once the session is over. So I am going to just share my screen. We are done with Pear Deck now. I am going to go through the rest of this just by sharing my screen on Zoom. So give me a second. to find my spot. Okay. All right. So I hope that was at least a little bit helpful. I'm sorry that you guys don't get more time to work together. I try and get through the setup as quickly as possible, and then the activities you get like 10 seconds for. So again, if you have questions or want more help, you can stay now. You can email me. I'm happy to meet with you guys another time in a smaller setting if you have some questions or concerns. So as far as NGSS alignment goes, this one should have been pretty clear. We were working with SEP2 and SEP4, but I just want to point out that anytime you're doing any of these SEPs, they're going to be embedded within an activity. And so you want to make sure that you're very explicit about setting them up and following them up so that students are not only using the skill, but they're using the skill to link to the anchoring phenomenon or the phenomena in general. So we don't really have a lot of time, so we're not going to talk about this in depth, but I want you to think about some of the backpack artifacts that could come out of doing this kind of work when students have become more responsible for their learning and start to engage more and feel more excited about doing this learning and discovering on their own and being able to link this to bigger ideas, specifically this globally and culturally competent citizen. If we're choosing phenomena that are relevant to current events and stuff like that, then that's going to give students an opportunity to really create some artifacts that can fall into that globally and culturally competent citizen. So our focus questions today were, how can we design activities with SEPs that engage and support student sense making? And then how does student learning change when they use SEPs to engage in well-designed activities? So I want to give you a second to reflect on that and think about that. If you want to share, you can send in the chat or you can unmute anything that you may have added to your answers to these questions throughout today's session. So I just want to point out that this is kind of the follow-up to today's activity. So linking this to your learning and your knowledge of teaching. Just like any good activity, there should be a follow-up. There should be a time for students to reflect and think about how their learning or their ideas have changed and to link that to the storyline, in this case, the NGSS classroom. So are there any questions before we finish up? Oh, I have a chat. So thanks, Chris. Anything that can tie an activity into a student's own experiences will greatly aid in sense making. I absolutely agree. And that's something that we definitely need to be cognizant of as we plan these activities, designing activities, being aware that we are helping them discover instead of simply telling them. Huge shift in the way teaching is happening, but the most important, I believe, in the science classroom. Awesome. So again, see the agenda for some additional resources. I've created a list of websites that have some units that are grounded in NGSS or aligned with NGSS and grounded in anchoring phenomena. There's also some that just have some activities that are really aligned to the SEPs, and just a couple other things that I found that I feel like could be very helpful, but didn't really have time to discuss in this session. So feedback from last session, the last two sessions, some things that you guys wanted to see in future lessons. A lot of it was geared around NTI. And then there were some other things that you wanted to see as well. And I just want to let you know that Lacey and I are definitely planning to have a PD centered on, I just lost all my whole train of thought, on NTI and the science classroom. And so how, like, platforms you can use and ways to incorporate some of these same things into a virtual world, more so than the ideas that I've been giving you. But I do plan to have a couple other ones too. I'm still struggling to read the NGSS standards. And so I'm hoping to have like an NGSS 101 for people who feel like they could really use some help with just dissecting those standards and understanding those better. And I plan to have another one later on about planning and designing activities around explanations and argumentation, but those haven't been set yet. So that being said, if you want emails about these PDs that I'm hoping to plan and offer soon, there's a link here which should be shared for everyone now, so you can click that link when you get to when you go into the slides. Remember, the link to all the slides is in the agenda, and you can sign up on that form. I won't spam you or anything. I'll just send emails when we have a PD planned. And the soonest one that we have planned is this high school science instruction in the NCI world. So you'll also find a survey that's very helpful for me. Your feedback is super, super beneficial for me in planning these. So the link is in the agenda. It's also in the slides. So you can find that. And I would really ask that you do that. It's short, I promise. And if you have any other questions, concerns, or needs, feel free to email or tweet at me or Lacey, and we are happy to help you with anything that you might need. So a whole 6 minutes early, guys. If you need anything, please stick around. I'm happy to help out. Otherwise, thank you so much for joining, and I hope that this was at least slightly helpful for you. And good luck with starting this NTI world. So I'll see y'all later.